As you can see, we're going to be talking about the accumulation function. We'll get to that here in just a second, but that's really what we're doing now. We have talked about a definite integral. We know that definite integral relates to area, and we're going to be considering here a special type of area problem, and we're going to start with a function f of x equals 2, and we know that to be the horizontal line at y equals 2, and we also can graph that function here. We can see that f of x equals 2 is the same as f of t equals 2, which is the same as f of k equals 2. So it really doesn't matter what variable we use. That in fact we're going to see why we use something other than x, because it would get kind of confusing when we're dealing with the integral from 0 to x, or the integral from whatever to x of f of something, and we want that something to be something other than x. Nevertheless, here we see the graph of f of t equals 2. We know it's a horizontal line, and we're going to consider right now the expression here, the integral from 0 to x of f of t dt. So we know that the integral from 0 to some value of x would be the area between the curve and the x-axis, in this case the t-axis. Okay, so from 0 to, or even the, whatever, f of t equals 2, so f depends on t and this t-axis, but when we go from 0 to x, x represents a variable along this horizontal line. So let's see what that means. Okay, we have the graph, like I said, f of t equals 2. Considering this, it's a function of x. So as x changes, so we want to see here, as x changes, so does the value of the integral, the definite integral. So let's go ahead and just calculate a couple of these values here. When x is equal to 0, we know that we have the integral from 0 to 0, and the integral from 0 to 0 means that we're not accumulating any area, and so we know that that's equal to 0. Okay, when the upper and lower limits of integration are the same, we learned that earlier, that we don't have any area, so we have always a value of 0 for that definite integral. Okay, well now let's look at the integral from 0 to 1. So I'll write 0 to 1 in here, because you know that when x is equal to 1, the function's value is the integral from 0 to 1. Well, if we look up here, 0 to 1, what's this area? So it's the area of that rectangle. Well, we have the area of the rectangle is length times width, so we have 1 times 2, so that's 2. Okay, and then the integral from 0 to 2, so when x is 2, we evaluate the definite integral from 0 to 2, and the integral from 0 to 2 is 1 times 2 is 2, and each of those has a value of 2, so the integral from 0 to 2, there's an area of 4 now underneath the x, or the graph of f of t equals 2, and the t-axis. Okay, so we can see every time we increase x by 1, we add. Let's see if I can put that in there. Do I have any other markers? I have no more markers here. Boy, what a travesty. So each of these has a value of 2, 2 here, 2 more, 2 more, and so we can see every time x increases by 1, the area increases by 2, so we know that when x is 3, the area between the curve and the x-axis is 6. When x is 4, we have 8. And when x is 5, we have the entire area of this region here from 0 to 5, and then the x in the t direction, and then from 0 to 2 in the y direction, and that would be 10, right? So 5 times 2 is 10. 2, 4, 6, 8, 10. All right. So it should be apparent that it says here that as x gets bigger, the value of the integral increases as well. Okay, so that's good. That's a good thing to be recognizing. Here, as x gets bigger, the integral increases as well. And what we appear to be doing is accumulating area. And so that's why we call this integral the accumulation function. Okay, because you're accumulating area. And then maybe now it's obvious why we use f of t instead of f of x, because when you have an x here and an x here and an x here, that would be confusing. Maybe it might not seem like it would be confusing, but that's why we do it. We use a different letter there. Okay? So I want you to pause the video and fill out this chart down here at the bottom. Okay, you should have a 0 here, and then from 0 to 1, the area of this is 1 times 1, which is 1. Cut that in half, so we get 1/2. Okay, 2 times 2, what is this? Doesn't necessarily say what the function is, but it doesn't say what the function is, but I'm going to assume here that this is the y equals x. Okay, so anyway, 2 times 2 is 4, divide that by 2 and you get 2. 3 times 3 is 9, so we get 9/2 for the area. Okay, and then 4 times 4 is 16, so we get 8. Okay, so 1/2, 4/2, 9/2, 16/2. Anyway, those are the values that you should have gotten. I'm going to go ahead and stop the video there, and we'll pick up page 148 from the worksheets here on the next video.